in this again. And let's take a look at this. Okay, so the data that we're going to look at is the amount of hours that somebody stayed in the hospital. And we're going to look at the amount of antibiotics that they're taking in milligrams per day. And we're going to look at the age of the person. And if they took this medication, does that increase or decrease the amount of days that they're actually spending in the hospital? So I want to keep it consistent. I don't want to change it up and go to a different one. And then we're like, what are you doing there? What's going on with the page tab? I believe my thing just froze. Stop sharing. Let's do it again. Okay. It's working now. Screen. Sharing. Can you see this, Tim? Okay. So we're now going to run regression, multiple regression, and we're looking at this data. And this is like how many hours you're spending in the hospital. And this is how many milligrams of antibiotics they're taking. This is their age. And this is if they're taking that new medication or not, that one that's supposed to cure them. And let's take a look to see, because we're seeing like, does this like decrease the amount of time that they spend in the hospital? Okay. Okay. So now we're looking at the time that they spent in the hospital based off of their age, based off of if they're taking antibiotics, right? If they're being given antibiotics, and if they're taking that brand new medication, what does that mean, right? Time-wise. And we're looking in hours of how long they spend in the hospital. Okay. And so looking at this model, this tells us how strongly correlated is antibiotics, their age, and the type of medication, and if they're taking that medication, how strongly correlated is that to them spending less or more time in the hospital? How strongly correlated are those things to the hospital stay? R-square is telling us how much does increasing or decreasing antibiotics, their age, and this medication, how much does increasing or decreasing that increase or decrease their stay in the hospital? Right? And this is saying 87% of the increase or decrease in their hospital stay has to do with the increase or decrease in antibiotics in their age or the amount of medication that they're taking. That's what this is telling us. Okay. Our adjusted R-square is our R-square after adjusting for, remember those slopes that we had? And we did that. So we want to adjust for those three slopes and all the data points. So if we adjust our R-square for all those changes that we made, that's our adjusted R-square. So our adjusted R-square is our R-square after adjusting for antibiotics, age, medication, and our sample size is telling us that 84% of the increase or decrease in antibiotics in their age or in this medication, how it increases or decreases their stay. Because maybe we decrease the medication, their stay's longer. Or we increase the medication, it's less. We'll see how that works out. What this is telling us is when we forecast how long their stay is, it's going to be off by about 25 hours, about by a day, roughly, a little bit more than a day. How many observations? Roughly about 15 people, right? This again is an ANOVA that we spend a tremendous amount of time on. That's our degree of freedom. Why? Because we have 4 groups. We have our antibiotics, age, medication, and how many hours they're going to stay. So our degrees of freedom is -1. That's our sum of squares, mean of squares. That's our F, that's our significant F. This is associated with the p-value. That is our p-value, but we know that if we increase that, it's not 0. And so we can write up a hypothesis now, and our hypothesis would say that B1 equals B2 equals B3 equals 0. And our alternative is at least 1B does not equal 0. At least one of them's a slope. What it's telling us is that, hey, 1, 2, and 3 all equal 0, right? So they all equal each other, but none of them are slopes. And the other one's saying like, no, one of them equals the slope. And when we look at the values of our B's, 1, 2, and 3, the value of B1 is 18B. That's the value of it. The value of B2 is 19B. The value of B3 is 20B, but we're saying that those all equal 0. And so what that significant F is telling us, hey, do we have a multiple regression model here? Is at least one of those a slope? And with that p-value of 0, 0, 0, what's that? 3 zeros? 4 zeros? 1, 2, 3, 4. 4 zeros, I believe. So p-value of 1, 2, 3, 4, and then a 2, our level of significance of 0.5. We can definitely reject that null hypothesis, and we'd be 99.998% confident that one of these is not 0. Does that seem similar to the ANOVA? Where the ANOVA said, like, when you reject the null, it says one of them's different. That's exactly what this is doing, because this is an ANOVA. That's why we see ANOVA written there.
Professor, so only one has to be.
It could be more than one.
Yeah, but like one has to have a slope in order for p-value to be below 0.5.
That's it, at least one. And what we're saying is at least one. Later on, we need to check, okay, well, which one? The Tukey-Kramer did that for us in the ANOVA.
Can we just check the p-value of each coefficient?
We're going to do that. But right now, what we're saying, at least one is not equal to 0. We may want to check to say, okay, well, which one? That's what we did with our Tukey-Kramer, right? It's the same as it, because it is an ANOVA. So we're saying that B1 equals B2 equals B3 equals 0. And at least 1B does not equal 0. Which one? So now we're going to need to test to see which one doesn't equal 0. So we're going to write a hypothesis for each one. B1 equals 0. B1 does not equal 0. B2 equals 0. B2 does not equal 0. B3 equals 0. B3 does not equal 0. We need to check each and every one. And so how do we check those? We're just going to do a t-test. Just like we did earlier when we learned about a t-test, but we need to check the value. We need to make sure that our p-value is okay. We're going to do that later on in our assumptions. But so now let's check, because we said at least one of them's a 0. Which one?
Okay.
So now if we go to our p-values for our each one of our coefficients, that would be E17, E18, E19, E20. And so B0 is E17, but that's an intercept, so we don't worry about that. So if we look at E18, which is antibiotics, is that a slope? So what we need is for it to be below 0.5. So when we look at our p-value, it's like 0.95, which means what? It's not below 0.5, which means that that's not even a slope. That one's not even a slope. Antibiotics is not even a slope. As you increase antibiotics, it does nothing. Okay, well, let's look at age. Okay, level of significance. So age is 20E. Our level of significance is 0.5. Our p-value is 28. Did we reject the null? No, right? P-value is too high. P-value has to be below the level of significance for both of these. So you didn't reject the null for antibiotics. So the null says that there is no slope. The alternative says there's a slope. So guess what? There's no slope for age and there's no slope for antibiotics. We're not going to reject the null, which means that neither one of them does anything. Increase or decrease the age, increase or decrease the antibiotics, and it does not get them out of the hospital any sooner. The medication, although, that p-value is nearly 0. It's showing 0. I'm sure if we put some numbers in there, we would eventually get a number, but I'm just going to say it's 0. We can reject our null hypothesis and say that there is a linear relationship between taking that medication and getting out of the hospital sooner. The medication, guess what, is working. And age and antibiotics, they don't really affect it, is what this is telling us. And so when we start looking at the coefficients, we say that, hey, if somebody wasn't taking antibiotics, age wasn't a factor, and they weren't taking medication, they would roughly stay about 351 hours. For every antibiotic they take, they stay about less, it's going to round those off to whole numbers, about 4 hours, right? Looking at age, for every year they're older, they stay 5 less days. Why is that? I don't know. But that's what our data is telling us here. So age isn't a bad thing. And with medication, for every, if they take medication, they actually stay 116 less hours, which is a lot based out of 351 hours. Oh my God, that is definitely working. That's what this is telling us. So if we were to write the equation for this model, it would be the amount of hours that they stayed is equal to 351 plus -4 plus -5 plus 116 plus or minus 25 hours. And that medication is a positive number. So in this case, even though I'm treating it as a negative number, it would say that we're actually going to stay more hours.
Professor,
Right? Yes.
why did you put the period to the left or to the right for antibiotics and age, but for medication you didn't put it?
The period.
So like antibiotic, it says that coefficients there is like -0.4, which we conclude that 4 days.
Yeah, I just rounded it off to 4 days instead of like, or 4 hours, sorry. Those are hours.
Oh.
Right? Those are looking at hours. I just didn't want to say like, what, 4 seconds or something.
Okay.
So I just wanted to round it off to 4 hours. The other one's 5 hours per year or whatever of your age. This one right here, see the 116? It's supposed to be, if you take the medication, you stay 116 more hours, but just for our understanding, I'm going to say that it's a negative number. I hope that doesn't screw with anybody's head. Are you getting that? Why I'm doing that?
Also, isn't the negative like negative 0.4 is a negative slope? Doesn't it means that that actually antibiotic would decrease the stay?
It does by 4 hours.
But then medication would increase.
Increase it, yes, by 116.
So it would actually be bad.
It would actually be bad. And that's why I
Okay.
said I'm going to treat it as if it's a negative, just for us to have something to talk about.
I get it.
But it would be bad. Medication would be bad. Actually, antibiotics would decrease the stay by 4 hours. For every year that you're older, would decrease it by 5 hours from 0 years old. And medication would actually increase your stay by 116 hours, is what the data is telling us. Right? And that would be this equation. That's exactly written out that way. Right?
Yeah.
So far, so good. Okay. So this is written out exactly how it shows there. So B0 is 351, B1 is 0.04, B2 is 0.5, B6 is 116, right? And our standard error is plus or minus 25. So far, so good? That's what our data is telling us.
You
Now,
get
our
the 25 from the standard error?
Yeah, standard error.
Okay.
So see that, and that's the, so that's a standard error up on the top. And so that's a standard error at B7, not the standard errors for each one of the slopes.
Okay, thank you.
And so the standard from each one of the slopes is kind of averaged out to what that means for the entire model. And that's what the standard error is on the entire model. So based off of this, we can actually calculate how long somebody would stay in the hospital. So far, so good? Based off of this model. So now let's start breaking it down step by step. Okay, now that we see this, we can solve this. So I'm going to show you a few other things in here. We can use this tool to put in the value for the antibiotics, if they get medication, and how long the stay would be. So imagine if antibiotics given, 5. Oh. Age, you have somebody that's, I don't know, say 25. And if we enter, we see how many hours it would stay. Now imagine if we give them antibiotics. Stay increases because antibiotics is a bad thing. We take away the antibiotics. Stay decreases, right? Increase, or sorry, I mean the medication, increase the antibiotics, and we can see where we get a little decrease there, right? Increase the age. Okay, and that's what this is doing, is forecasting based off of those coefficients. But this is telling us, various inflation factor is that if we're double counting data and how much our data is being inflated by. It's called multicollinearity, and if our VIF is below 5, then it's good. So this is measuring medication against all the rest. This is measuring age against all the other variables. And that's measuring antibiotics against all the rest, and we're not double counting anything. See this right here? The reason why I like this little feature where it's like the Knox 3s is, remember on the other one, how we had antibiotics, we had age, and we had medication? What this did was it actually removed medication. And after we removed medication, we can now see if these two are slopes. So it just plays around the model just to see if it actually helped. And when we look at this one, like the overall model is not even good. We look at the p-value and we notice that antibiotics and age by themselves, neither one of those are slopes. We look at this one and we're looking at medication and antibiotics. And we notice that medication works by itself, right? And medication's a slope. And this one right here, also we notice that medication works, but age doesn't. Okay.
What, Professor, why are the p-values for age changing in each of the,
Why are they?
yeah,
Because it's when you're coming up with the intercept for each one of those data points, it affects
okay.
it affects the intercept and affects the slopes themselves. And it affects the p-value, if they're a slope or not, and the p-value for the entire model as well. And so I'm going to look back at the VIFs again. So a VIF is if you're double counting data, right? Imagine if I'm looking at antibiotics, and when I'm looking at antibiotics, I'm looking at subgroups of antibiotics, and I'm looking at, oh God, a Z-Pak versus erythromycin or something. And I'm looking at two different antibiotics and I add them together, then they're both antibiotics, but they're different antibiotics. And if my measure is antibiotics, then I could be like double counting, right? If I say antibiotics and then I say erythromycin, then I'm counting that twice. And then what that would show is my numbers are being inflated because I'm counting, I'm saying antibiotics, and then I'm saying erythromycin, which is an antibiotic, right? And that could throw the numbers off. And that's what it's, so 5. So variance inflation factor means that you're inflating the end results. And so we don't want to see it above 5.
Above 5 or 1.5?
So above 5. Say that
above
again.
5.
Yeah. Multicollinearity. Yeah. So you include it, but you want to look at it just to make sure that your data is not inflated. But the assumptions is only because with the assumptions, you want to make sure that the lines are lines, standard error is good. So you're looking at the basic Excel sheet and you want to validate all that data. But this is just the overall model as well. I don't know, did that help or no, or mess you up? Okay. So looking at those. That's our Durbin-Watson. That's our residual plot for medication. Either they took it or they didn't. Remember I said if it's categorical, you can't get a pattern out of it. And that's what that is. We're going to write this up in just a second. For age, because we only had a few different ages there, 35 and 40, so it wasn't really spread out. And this is for antibiotics. Residuals versus plot. So we can also run this and get our skewness and kurtosis out of it. So we're going to write this up in just a second, and it should take us 10 minutes. Labels in first row, summary statistics. And so when we look at our skewness and kurtosis, it's okay, which means that our p-values are okay for the overall model and the p-values for each and every slope. Okay. Fruitful for you, or you got to go?
Yeah, I gotta go, but it was very helpful.
Okay.
Yeah.
Good, good,
I'll
good.
probably check out the YouTube just to get the last part of it.
Okay.
Yeah.
All right. Let me know. All right. We'll
Solid.
post it.
Yeah, thank you.
Oh, you're welcome. So skewness and kurtosis is okay, which means our p-value is okay. So linearity, we're not seeing any curvilinear patterns in there. Independence, Durbin-Watson is okay. Normality, skewness and kurtosis is okay. And so the last thing we want to look at is equivariances. And then we'll write this thing up. Does it shift? Okay, what's it doing? Okay, insert. What we don't want to see is a wedge pattern, and I'm not seeing one in there. So what this is telling us is that it's equally variable over time. We're not seeing it increase, right? And it would start, if it did increase, it would start from the 0 and start increasing over time. But it's looks like it's equally variable on both sides. Its patterns are, right, no wedge shaped pattern. So our assumptions are okay. Except for there was some issues with the slopes themselves. Some of them weren't slopes. So now we can write this up. Who wrote it up last time? Somebody else used their computer? Was it you, Maria?
Yeah, it was me.
Do you want to?
Yeah, I can.
Okay, and then I'll dictate it as you write it up, so you can share your screen. You can hang on. Let me write down some of these numbers. P-values 1, 2, 3, 4, and 2. Our R square is 87.
I just have to share my Word document, though, right?
Yeah, just show the Word document. 25 and intercept 351. Antibiotics is 4. Age is 5. And medication is 116. Okay, go ahead, share your document, and I think that we're okay. And we can write it up and try to make sense of this.
Which one are we gonna be writing about? Sorry, I had to go to the
So the regression one. So use the same document, go all the way down the bottom, and the regression should be on there.
Okay.
So not bad. In about 3.5 hours, we've got through the entire semester. Huh? Say that again? We're gonna do chi-square, yeah. Are you working on that, Maria?
Yeah.
Okay.
Wait, can you guys see my screen?
No, I think, oh, sorry.
Oh,
We're gonna have to stop
okay.
sharing.
Sorry.
Okay, go ahead. My bad. No, you're okay.
Okay. There.
Okay. So we're going to change this. And so it was B1, B2, B3 equals 0. So it was hypothesized that antibiotics, age, and medication would not affect the amount of time you stayed in the hospital if you had COVID. So antibiotics, age, and medication would not affect the amount of time you stayed in a hospital if you had COVID.
Still recording, right?
I think so, yeah. There is significant evidence to reject the null hypothesis. Significant F was at 0.00004 zeros and then a 2, which is below the level of significance of 0.05. Yep, 0.05. I am 99 99.998% confident that one of the slopes is not equal to 0. And then we'd say 87% of the increase or decrease. And this treatment, these treatment options are attributed to the independent variables. When you adjust for
Antibiotics.
antibiotics, yeah, age and medication. And the sample size, the percentage went to 84. The slopes for the independent variables, coefficients, indicate if somebody used antibiotics, their stay would be 4 hours less.
They're what?
Their
Yeah.
stay at the hospital or would be 4 hours less. Oh, wait, okay, we did, sorry, my bad. We did not do the intercept. Okay, so that part, we have to add something in between that. So the slopes for the independent variables indicate that if somebody did not use antibiotics,
Oh, did not? Okay.
yeah, if somebody did not use antibiotics, if age was not a factor and they did not use medication, their stay would be 351 hours. So if everything was 0, basically, their stay would be 351 hours. And for every pill they took of antibiotics, their stay in the hospital decreased by 4 hours. And for every year that they were older,
By 4 hours, right?
yeah.
Okay.
And for every year that they were over 0 years old, I guess, they stayed 5 hours less. And if they took the medication, designed for COVID, they actually stayed 116 more hours.
So I can delete this, right?
You can delete all that, yep. To validate the models, we check the assumptions of linearity, independence, normality, and equal variances. The assumption of linearity was okay. We didn't see any patterns. To verify independence, we checked the Durbin-Watson. I believe it was 1.9. So the assumption of independence is met, which means that our standard error is okay. To verify the assumption of normality, we checked skewness and kurtosis, and that was both within normal range. To validate equal variability, we checked residuals plotted against predicted, and there was no wedge-shaped pattern, indicating that the data was equally variable. The overall model, the overall error, sorry, in the model was 25. The independent variables of price, advertising, and holiday. Yeah, they did not have p-values below the level of significance. The only one that did was medication. Yeah. So you need to remove those. So they should not be removed because they should not be included. Right? So those variables should not be included. But medication but medication had a p-value below 0.05. So it should be included in the model. The various inflation factors is below 0.05, indicating multicollinearity is not significant in the model. That right there would get you full credit for a regression write-up. And that right there, if you were answering any of the questions on the regression tests that we seen last time, literally copying and pasting them, except for it wouldn't give you the, it would give you the hypothesis, but it wouldn't give you like the equation, right? You'd have to write that equation in.
You mean like the y equals
Yeah,
intercept plus
that's
slope?
it. Yeah, you'd have to write that in for that question. But for most of the other stuff, that would answer the question. Okay, so far so good. And so that's kind of one of those ditch efforts to get you guys to understand regression. So I'm going to stop recording.